All right, hi there. Have a look at these faces right here. So you're probably used by now to seeing computer-generated faces of really high quality, but probably you're used to seeing these faces coming from a generative adversarial network. However, these faces right here are from a variational autoencoder. Now, variational autoencoders are fundamentally different than GANs, and traditionally they've been a bit harder to scale up to high-resolution images and give sort of very detailed, sharp output. This paper right here attempts to build such a VAE for these high-resolution large data set. And it basically details everything you need to do to get a VAE like this. So the paper is called NVAE, or NVAE, I don't know how to pronounce that, a deep hierarchical variational autoencoder by Arash Vedat and Jan Kautz of NVIDIA. As I said, on a high level, this paper is about how to build a deep hierarchical variational autoencoder, which is sort of a combination of already existing techniques combined in a clever way, and then listing all the engineering efforts that you need to do to actually make this work. And there's not one thing where you can say, this is the thing that really made it work, but each of these techniques is going to stack and stack and stack until they reach a model that surpasses the state of the art on these data sets. And they are also able to apply this to an entirely new high quality image data set. So these again are some of the samples from that model. And as you can see, they look very, very crisp, very sharp, and also very, let's say, real. Yeah. So really briefly, variational autoencoders. So this paper attempts to build a variational autoencoder. What is it? For that, you need to start with what an autoencoder is. So an autoencoder traditionally, let's say you have an image data set, and you take an image and you train a model that consists of an encoder that maps your image to a lower dimensional space, a compressed space, which you call the latent space Z. And then you train a decoder to, again, go from the latent space back to the image space. And then you train those two models such that the distance between the output and the input is minimized. Okay, this is called the reconstruction loss, and you train the encoder and the decoder to minimize that reconstruction loss. And thereby you hope that this latent space will learn something about the data, let's say. Now, a sort of advanced version of this and a probabilistic version of this is the variational autoencoder, where we say what we want to do is we don't want the encoder to just output directly the latent code, but we interpret this in a probabilistic fashion. So the encoder is now a probabilistic function that outputs a distribution over latent codes. So we take our same image, and what we want to do is we want a Bayesian, basically it's a Bayesian way of thinking of it, we want a distribution over latent codes corresponding to that image. So our encoder here is not going to output Z, but is going to output mu and sigma. So it would be ideal if it could output an entire distribution, but we're going to make some assumptions here that that is a normal distribution, and it's going to output the mean and the standard deviation of that normal distribution. And then you actually, because now how are you going to feed this into the decoder? If you just feed mu, you are back to the normal autoencoder, so that doesn't work. What you do is you actually instantiate that normal distribution with the mu and the sigma, so you plug that in here. You sample one sample from that normal distribution, and then you feed that sample into your decoder. Again, your decoder outputs an image from that sample, and you compare this with the reconstruction loss. And now you train the entire process. So you train the encoder and the decoder to produce to reproduce these images correctly. Now, if you only do that, then the model will basically regress to a standard autoencoder. Why is that? Well, what's pretty easy you can see that estimating the distribution is harder than estimating just the latent code, at least for the training data set, right? So if you don't pay attention, what the encoder is going to do is it's going to say, oh, well, if I just make this here my latent code, and if I just make this as small as possible, like 0 or like 1 to the minus 10, 10, that's still 1, 10 to the minus 1, that's not that small, 10 to the minus 10, 11, 12, okay? A very small number. Then that normal distribution will basically be just spiky around my mean, and so this here will always be kind of the same z, so it won't be a distribution at all. It will just be this Dirac, and I'm back to the original autoencoder, which I don't want. I want my probabilistic framework so I can compute likelihoods and so on. There are various advantages to having a probabilistic view of the data rather than just a model that produces it. Okay, and that's why in a VAE there is not only the objective, not only this objective, the reconstruction objective, but there is a second objective where we say that we impose a regularization, and the regularization is that this here is as close as possible to a standard normal distribution. And I guess you can choose that, the prior, but in regularly you say, okay, this here, I don't want you, encoder, I don't want you to go far away from a standard normal distribution. Like, do what you have to do to make the loss small, but don't go away too far. All right, so that's the kind of balance in the VAE. And as you can imagine, if you have a normal distribution and you sample these z vectors here, and the reconstruction loss is always the same. So if you input the same x here a bunch of times, you'll get different z's, right? You get z1, z2, z3, because it's sampled from this distribution. There's a sampling procedure right here. So if your discriminator here is kind of smooth, then it will output different images. Now, these images will always be compared to that same input image, right? So you're training this whole architecture to always reconstruct that input image from different images. So there is an interaction, I think that's what's happening. I guess I'm not an expert on VAEs, but this here usually is something like the L2 loss. So in terms of how this affects the images, if I have different images that are sort of the same but sort of different, and I have to make it L2 loss close to this image right here, then one option I have is to make them kind of blurry. So if I make all of them kind of blurry in the L2 loss, that will give me a lower penalty. So that's, I believe that's one of the explanations I heard at some point, why VAEs produce usually blurry images. And that's been a problem for a long time, that everything's kind of blurry. So here, the hierarchical VAE comes to the rescue. So how they are going to battle this problem is by doing a hierarchical variational autoencoder. And this is how it works. So you start off, this is your generator. By the way, once you've trained your VAE, right? Once you've trained it, you can simply sample from your prior, from this here, because that's, close enough to this. Or you can, I guess, learn the prior of your data distribution and so on. And you can just use the generator right here, the generative part. This part right here is your generator in order to produce images. So you can sample from a VAE like you could sample from a GAN. Okay, so here we'll look at a model that could combat those things. On the right side, you can see the model that you would ultimately sample from. So this is going to be your decoder, okay, this generative model right here. And what they do is, it's very similar to, NVIDIA also had this paper about this GAN where they are on different scales, like progressive, I think prog GAN, which was the first that introduced actually this high quality phase data sets, I believe at least. So here we're going to do a very, very similar trick. So the idea is that we start out, this is a learned quantity, but you can also view it as just kind of the zero vector. We start out with our noise. We sample our noise, but our noise is going to be, let's say it's in the shape of an image. We can do that. We can reshape images, right? So it's going to just be a 16 entry vector, and it's going to be shaped like this, okay? We sample noise like this, and then we produce an image of 16 by 16 from it. I think they start with 8 by 8 or something like this, but conceptually, you do that. Then you have a neural network. This is a residual neural network. Produce an image out of that noise, right? It maps the noise to the image. So this is your D, your discriminator part. But then you're not done. What you do is you would actually upscale that image, or that can happen in the neural network, I believe, or you are upsampled from the beginning and you enlarge these things. But what you would do is you would upscale your neural network and you go higher. And so on. So you go higher and higher and higher in the hierarchy of noises. So this is a hierarchical model. Oh yeah, down here. So they start from, as you can see, it consists of 36 groups in their case of latent variables, starting from 8 by 8, scaled up to 128 to 128, with 2 residual cells per latent variable groups. Okay, so you continuously scale and scale and scale up your images, and each time you add another bunch of these noises right here. So that means that in this model, the uppermost residual model can sort of get the coarse details of the image. And that's going to be blurry because it's a VAE, but it's going to be blurry in that coarse scale. And then you upsample it and you let another model add on top of that the next layer of features. You can see this is kind of a residual connection right here. And you again sample and you let another neural network upsample, let another neural network add more features in a higher resolution. So even though each VAE can be blurry in its own scale, it will be upscaled, and there will be additional details added. And that's why in their samples you will see that they're not super blurry at all. Though I have to say something right here. If you look at these images and you compare them, so later they compare them, they almost look like puppets, right? So here you compare it to, these are previous methods down there. Now, to say that you can see they're clearly kind of worse in that you can see the symmetry of the faces aren't really given, also the symmetries. Here there are no long-range dependencies. The hair details are often missing as compared to like here. This is pretty crisp. But if you look at like the skin of people and just kind of the image composition in shadows, it looks like these people are like cardboard cutouts. Here they have like these multiple layers where I mean, am I the only one that just sees this? This is like a plastic cutout, and then the face is again like a plastic cutout, and the faces are so smooth. I mean, look at this. These are like two pretty, like you can just look at this for hours. This is so like maybe it just seems like this to me, but the difference if you kind of look at the skin, and it almost feels like the bottom ones are actual real photographs in terms of the faces and the kind of the color, just the smoothness. It just all look like porcelain. This might actually be an effect of the VAE, right? Because it's not blurry, right, as the lines and so on, but the skin texture might just be one scale too much here, and that's where we now see the blurriness. Or it might just be that I don't know. Okay, I have no idea. This just somehow was popping out to me as the main difference. Like, they are much more crisp and so on, and much more beautiful, but also they look like puppets. Yeah. All right, so let's get back to the model right here, because so once we decided that we want such a hierarchical model, what we need to do is we need to simply build a VAE for each of these hierarchies, right? So the uppermost thing here is a regular VAE noise, right? We have a noise, we sample from it, and we generate this particular scale of image. Okay, so how do we get that noise? We simply, this down here is our encoder, and this is our decoder. We simply have our encoder. This is a series of neural networks, and we get our latent encoding, right? So the Z is obtained through the kind of VAE encoding method. Okay. Now the interesting part is, how do we get Z2? And you might just think, well, we'll just go like one layer up here. But Z2, as you can see here, it depends on Z1 during sampling. So during inference, we also have to have that Z2 depends on Z1. And that's why we first need to go to Z1 and actually produce a sample. So our method of inferring the latent codes includes already sampling from those latent codes, right? So you sample and you do the same thing as you would do on the right. In fact, these models are shared. And then you can see that Z2 now depends on Z1 in this procedure, because you go here and you go here and here. So Z2 depends on Z1. Z3 in turn would depend on Z2 and Z1. And you have a properly hierarchically factorized model right here. Okay, so this is called a hierarchical VAE. It pretty much works like a VAE, except that it is hierarchical, and you need to have this bottom up and this top down model in your encoder. And so now there are a bunch of questions with respect to the hierarchical VAE. The problem here is that you have not only one sampling procedure, but you have sampling procedure upon sampling procedure upon sampling procedure, and this can get pretty unstable, I guess, pretty quickly. So the rest of the paper is going to be how to get this to work. So the main, I think, one of the main parts they do in order to get this to work, in order to get this to train, are residual connections. So we know that residual connections are kind of a sort of a gradient flow highway in order to train very deep networks, and we've already seen this with residual networks in CNNs, where you have an input and you have some computation in form of a neural network, or in this case, a sampling procedure through a distribution, and you have an output, and the residual connection would allow you to skip part of that. As you can see, used here in both the encoders and the decoders. So in the encoders, you have residual connections, and also in the decoders, right here, you can see you have residual connections. In fact, you always take that lower scale and you don't transform it into an upper scale. You actually sample noise, and then you add the lower scale and the upper scale together. So it's really an additive model in a hierarchical fashion. Even, okay, the pluses might actually not be, okay, the pluses can also be combination, I guess. I guess that I might be wrong, and they can actually be combinations. In any case, they use residual networks in a lot of cases in their generative and in their generator and in their encoder. You can see right here, there is a residual cell for the generative model and a residual cell for the encoder. Now, the exact method of these residual cell, you can see that they use batch norm, then they use 1-by-1 convolutions in order to go to a higher channel number before they do the depth separated 5-by-5 convolutions. So 5-by-5, because you need a larger receptive field. They make that clear. They need a large receptive field. However, the large receptive field means many parameters, means their model would be too big and too much memory. So they do the depth separated convolutions, which simply means that you don't mix the channels during convolutions. So you go up the channels, you do a depth separated convolution, and go down the channels again. All of these are kind of hacks to make it work, right? Then also they have batch norm and a swish non-linearity, as you can see here. And then here as well in the encoder, they also say in the text, like they stress the importance, we found that first the batch norm and then the convolution is better than the other way around and so on. So there's a lot of engineering work that went into this right here. So you see there's batch norm, and also you have to kind of hack the batch norm, because in batch norm you have these training parameters, and people have observed that in VAEs, if you, during inference, during sampling, if you use the training way where you only regularize within the batch, it's better than if you use the running averages. So you kind of have to hack that. We modify the momentum parameter of batch norm such that running statistic can catch up faster with the batch statistics. There's a lot of engineering in here. Like there's a lot of things that you have to get right to get something like this to work, apparently. And yeah, the paper just goes on in this style. So you can see they use the swish activation. They use squeeze and excitation blocks, which are another form of residual blocks that were introduced quite a long time ago, but still being used, as you can see. And yeah, so that's the architecture. So you can see they have residual cells there, residual cells here. Reducing the memory requirements, they say they use two tricks. First of all, they do mixed precision using a cool new NVIDIA library. Like, given that they're from NVIDIA, they get to try these things out first. And second of all, they also, to reduce the memory, we fuse batch norm and swish, and we store only one feature map for the backward pass instead of two. And they have to then recompute. This trick is known as gradient checkpointing. It requires recomputing batch norm in the backward pass. I believe like future deep learning frameworks should just take care of that for you instead of you having to do this kind of stuff, honestly. So they also need to, they say taming the unbounded KL term. So the KL term is what makes the distribution that the encoder outputs close to that distribution that you want, like that normal distribution. So this is the regularization term. You can see here it's a KL divergence between Q, which is what your encoder outputs. You can see that's the latent code for the image X. Between that and between your prior, which you say it should be a normal distribution. In this case, it should be a hierarchical normal distribution. And they have a special characterization here where they say, because it's hierarchical, right? So what does it mean to have hierarchical normal distribution? So I'm going to have a hierarchy of normal distributions. This is my top hierarchy. And then I'm going to sample one sample right here, right? And then in the next layer, I'm going to have a normal distribution around that sample right here. And I'm going to sample from that, and so on. So my hierarchical normal distribution is going to be always where the next distribution in the next layer is dependent on the distribution in the higher up the hierarchy. And they have a special parameterization where in order for the encoder to produce that, so the encoder has to produce a Z of the first layer and then a Z of the second layer and so on. In order for the encoder to reproduce that and to be close, it must match this distribution and it must match this distribution. So if it doesn't match this distribution correctly, it will kind of sample somewhere else a bit, right? And then that distribution, that base will already be shifted right here. So it thinks that the distribution to match is now this normal distribution. So you can see that the base is already shifted, and that's why their encoder only outputs the delta to the, as you can see here, it only outputs the delta to the prior. We define the Q of the Z in a given layer as the normal distribution of the mu I, with mu I, that's your prior, see, that's your prior of that layer, plus a delta mu. And also the sigma is the sigma from the prior times a delta sigma that you output. So you're kind of saying you're not supposed to output the actual distribution, you're supposed to output the difference of distribution to the prior. Now in layer 0, that's the same thing, right? Because the prior is going to be zero mean and unit variance. So that's this here will be 0 and this here will be 1. But in all the upper layers, this is going to make it easier. So that's one trick you have to make this repeated sampling not hurt you as much. The other trick they employ here is spectral regularization, which is a regularization where you regularize the top singular value per layer. You can use that, you can compute that with a power iteration. People have been doing this before, and also you can build in some normalizing flows, which, so here, if we sample the different layers, what we're going to do is we're going to sample all of these things at once, right? They're dependent on the upper layer in the hierarchy, but we'll sample them all at once. And that means they are not sort of connected to each other. Now, if we introduce a flow, we'll basically make them all connected to each other and build like a singular distribution of them. But I don't want to go too much into this because it doesn't gain that much. They say you can just build that in if you want. Okay, so these are all the things that at least they list in the method section. Now there are like a lot more that they have to do, but ultimately, as you can see right here, on 4 of these 5 datasets, they achieve state of the art. In fact, okay, on this dataset, no one else has tried, but at least on the other datasets, they are very, very competitive, as you can see right here. And they compare this to, first of all, to other models, and even other models with and without autoregressive flows. And they come pretty close to these autoregressive models. So an autoregressive model would be one that generates like 1 pixel at a time, conditioned on the other pixels. That this model doesn't do that. This model generates all pixels at once, so it's not autoregressive. But as you can see, it beats all the other non-autoregressive models, and it gets pretty close to the best autoregressive models, which are down here. They're still better, but the gap is kind of shrinking, is what they say. Cool, so that's the main result. Then they have ablations, where they basically, as I said, all of these things kind of contribute a little bit to building this bigger and bigger and deeper variational autoencoder. So it's hard to say what exactly makes this work, because all of it makes it work. And I guess they just kept going until they beat state of the art, or until, you know, they ran out of tricks. Again, these are the samples that we looked at, and I do want to spend some time in the appendix right here, because I think it's pretty interesting what they do. So first of all, they show that their model doesn't remember the training samples. As you can see right here, these are always the nearest neighbor from the training sample. So the model is fairly far away from the training samples. But yeah, I mean, okay, maybe it's just me, but the left, they just look like more idealized humans, like very smooth humans, like designer babies. Here they show that if you use batch norm as you would use it, I think, regularly, where you keep these running stats, or you do the batch norm from training, then you get into this kind of degenerate case if you sample at lower temperatures. So the temperature that you sample from describes the width of the Gaussian that you ultimately want to sample from. And if you do, they have this method to readjust the batch norm statistics, which I don't want to go into here, but you can read it up to basically fix that problem. It is a problem that apparently other people have observed as well. And their method apparently is one that manages to do that. Okay, lastly, there are some more samples right here. And yeah, this right here. This is honestly, this is I think one of the most interesting things, where they go, and since they have this hierarchical model, right? So here is like Z1, it gives and so that gets you like an image, and then there's Z2, and that gets you an image, and then there's Z3, and so on, and you continuously upscale and hierarchically add the features. Here they say, what happens if we sample Z1 once and then we fix it, and then we only sample the other ones conditioned on Z1. And here, see where you see top scale fixed. And you can see there is considerable variation in the image, but there is not really a large scale variation. Okay, so the general face keeps constant, but there are details changing, as you can see. So here the hair is kind of going over the image, the color is changing. Here there are a lot of changes. The mouth looks slightly different as far as I can see, but I might be hallucinating here. And then if you fix continuously the top 2 scales or the top 3 scales, right here, top 4 scales, you can see that there are more and more just little details that change more and more. So yeah, so this is, they are operating at 5 scales, starting from 8 by 8 up to 128 to 128. In each row, we fix the samples at a number of top scales, and we sample from the rest of the hierarchy. As we can see, the long-range global structure is mostly recorded at the top of the hierarchy in the 8 by 8 dimensional groups. The second scale does apply some global modifications, such as changing eyes, hair color, skin tone, the shape of the face. The bottom groups capture mostly low-level variations. However, the lowest scale can still make some subtle long-range modifications. For example, the hair color is slightly modified when we are only sampling from the lowest scale in the last row. This is potentially enabled because of the larger receptive field in our depth-wise separable residual cell. Yeah, the hair color changes, okay, slightly, maybe. I don't know, my eyes are too many faces, okay. But, what's certainly the case is that their models exhibit much better kind of global unity compared to these other samples, where you can pretty clearly see like the different sides of the faces have little to do with each other and so on. And this is the benefit that you get from doing this hierarchically. So you have part of your model that's responsible for kind of the global shape of the image, and then that keeps it consistent. And then you have other parts that are responsible for the details. Okay, so I hope this was something to, that interested you. I myself, as I said, it's an engineering paper. So there is lots of things described. There's not like one jumping idea. I guess residual connections are pretty important, and these depth-wise convolutions save memory. But also all of the other things that you have to do to build something like this are pretty interesting. Yeah, I hope you gained something from it, and I'll see you next time.